And that's the next part of my talk. I'm going to talk about the airfare search complexity, as in the formal complexity metrics associated with it. Before I go into this, let me give you a very quick crash course on complexity in case anybody is not familiar with it. Time complexity or space complexity essentially talks about how much time or space is required to solve a problem, and this time is a function of the size of the problem itself, as in how many numbers or how many units of data that you have to operate on. So the popular, I guess, complexity class is called P, or polynomial. So the P says that the time it takes to solve this problem is a polynomial function of the size of the input. Now the other one is called NP. NP, which stands for non-deterministic polynomial, which is a horrible name, by the way. But in any case, NP simply means that given a candidate solution to a problem, you can verify whether or not that candidate is an actual solution to the problem in polynomial time. So if a problem is said to be NP hard, if it is as hard as or harder than all the NP problems that you can think of. And then you have, in the space complexity, you have something called P-space, which says that the amount of, in some sense, RAM, memory that you need to solve this problem is a polynomial function of the size of the input. And EXP space says that if the amount of space that you need to solve this problem is an exponential function of the size of the input. And EXP space hard essentially says that this problem, the amount of memory needed to solve this problem, is at least as much as an exponential function of the size of the input. So with that, here's what we know. We know that even the most basic problems in flight search are hard. Say I give you a fixed route and I give you a fixed fare, and all you have to do is choose which flights you want to use to plan your journey. Even that problem turns out to be NP hard. Or let's say we fix the flights and we fix the priceable units, and all we're changing are the fares that you have to apply. Even that's NP hard. So you fix the flights, you fix the fares, all you have to choose are the appropriate priceable units. Even that's NP hard. The full search is known to be EXP space hard, and in fact, full search is Turing undecidable. Now, I don't have time to go through the proofs for all of this, but I will go through the two of them, because I think and the nice thing about these two proofs is that they just follow from very fundamental parts of airline pricing framework, and they're not that difficult to understand. So one thing you have to know that you've got two NP-complete problems. That is, problems that are both in NP and are the hardest problems in NP, which is satisfiability and graph coloring. Satisfiability says that given any sort of first-order logic expression, assigning truth values to it such that the entire expression is true is known to be in NP and as hard as any problem in NP. And graph coloring says, given any graph, assigning colors to each of the nodes in the graph such that no two neighboring nodes have the same color, even that is known to be in NP and as hard as any problem in NP. Now, why is this important? Because consider the first case where you've got a fixed fare and you've got a fixed route. In this graph, for example, the figure here, you want to go from airport A0 to airport AK, and you know that you're going via airport A1 to A2, A3, and so on. And the fare is fixed. You know how much you want to pay. It's just that each of these fares have multiple choices of the flights you want to choose. Now what I can do is I can reduce it from 3SAT. Assume you have a satisfiability clause. Assume the clause you want to satisfy is X1 or X2 or not of X3 and X2 or X5 or X6 and so on. So what I'm going to do is I'm going to build a flight path across airports. So what I'm going to do is, if I've got K variables, I'm going to use K plus 1 airports with A0 to AK with 2 flights between the airports. And each flight corresponds to a true or false value for each of the variable. And if I have M clauses, I'm going to say I have M fare roles. So here what I'm going to say, here as you can see, say A0 to A1, I have 2 flights. I have X1 being true, and the other flight is x1 being false. A1 to A2, I've got two flights. x2 being true and not x2 being false, and so on. Now, what you can see is that it's sort of easy to see this. The fare rules are just take that logical expression that I have and just take the negation of it and say, all right, so if it's x1 or x2 or not x3, then I just take the negation of it, with De Morgan's law and say, all right, so if not x1 and not x2 and x3, then I just fail. And then take the next expression, like x2 or not x5 or x6, I say not x2 and x5 and x6, then fail, and so on. Like, only if none of these things fail, then pass. What does that tell me? What it tells me is that the set of flights that I can use subject to these fare rules is essentially a solution to a truth values to x1, x2, x3, so on to xk, which satisfies the expression above. And we know that satisfying an arbitrary expression like this is known to be NP-hard. Therefore, even the simplified instance of the problem is NP-hard. So another example, like you've got the fixed flights and you've got fixed priceable units, and even that's known to be NP-hard, where the only choice is you have to select a fare per flight such that the set of fares are compatible. You even know what the flights are. So how do you do this? I reduce this from K coloring M-vertex graph coloring problem. Well, what I say is that take an arbitrary graph which has M vertices, and I want to color it using K colors. So what I do is I say, all right, so I map every vertex to a flight, so I have M flights, and every color to a fare. So if I have K colors, then I have K fares per flight. And there's for edges between vertices, which means that, if I have an edge from vertex I to vertex j, then the flight corresponding to vertex I is flight I. And I say that flight I's fares restrict flight J's fares. In other words, flights I and j cannot use the same color fare. That's essentially what the restriction says. Now let's see how this pans out, right? I've got flights from S to x1 to x2 to x3 and so on to xn. And each of these flights correspond to a vertex in the graph. And I look at the fares, right? So let's look at 3 coloring, because that's the smallest value of K for which K coloring is NP-hard. So we have 3 fares, red 1, blue 1, green 1 for, flight S to x1, which is, say, vertex 1. So for vertex 2, which is x1 to x2, say the colors are red to blue to green to, and so on. And then my flight restrictions essentially says that for any red sub I rules is that for all edges, you cannot use a red I fare rule with a red j fare rule for all edges I comma j. So essentially, if you can come up with a way to solve these fare restrictions, then you've essentially come up with a way to solve k-vertex coloring. But we know k-vertex coloring is NP-hard, so even this has to be NP-hard. There's no other way around it. So, what are we left with? It's very simple. Even the most basic of subproblems are provably hard. And these are not proofs of just some bad corner case that never happens in practice, and that it's just that these fare rules are inherently allow for so much complication that this can happen, but the airlines would never do such a thing. No, that is not true. These proofs reflect real algorithmic challenges. The complexity proofs, they're much harder than they look, right? Because the electronic format with these fare rules are defined are very complicated, but they're also very limited. So to prove that these kinds of behaviors are actually possible are not very easy to see. I mean, I just give you a very, very informal, intuitive explanation for why these results are true, but the actual formal proofs are hard. And what's worse is heuristics are risky in this case. I mean, you cannot just say, all right, I'm going to say, I know this is NP-hard, but I'm going to use some approximation to make this problem tractable. The reason is that these availability restrictions, fare rules restrictions, are there for a reason. The airlines are trying to solve an optimization problem, which is maximizing the revenue. So if you use a heuristic that actually works, then the airlines know that they haven't done their job well. So airlines can change their fare rules and structures instantaneously to make sure that such heuristics do not work. And sometimes they do it deliberately, which complicates the space. And so any heuristic that you use that may work today will stop working very quickly. So using heuristics is just very risky in this case. And naturally, the order of growth is a serious issue, especially when you don't have a tractable way of solving this problem. So how do you solve this problem? As you can see from this point, you cannot use heuristics. I mean, you cannot really guarantee optimal or an approximately optimal solution to this problem. So what do you have? Well, this is where Cubix comes in, which is a company called ITA Software, which Google acquired. It's their main search product. And the concept of the Cubix algorithm is as follows. Think of the sequence of flights, fares, priceable units in a ticket as a sentence in a hierarchical abstract language. And think of the set of valid results to a search query as being a set of such sentences. Now, which means that given these sentences, we can try to construct a compact grammar representing these sets. And we try to do it efficiently, starting with short clauses and gradually adding context. Although technically the grammar is not context-free, for the most part you can assume that it is context-free. And once you have context-free grammar, you can parse it nicely and you can sort of get nice properties out of it, through which you can get some sort of you can get reasonable answers to your questions. Now, there's no way to guarantee that you will get the best answer, but you can get a reasonable answer. But even this, even though it's in a quote-unquote compact grammar, it's not really that compact from a human cognitive abilities point of view. For example, here's a sample grammar for a toy problem. It doesn't make much sense, but to you just at a glance, but think of it this way. It has, what are the clauses it has? It has an AND clause and an OR clause. And it also has fares and it has flights. So essentially what it says is, an OR clause says pick any one of these two or any one of these N, and an AND clause says pick all of these to construct a sentence. Like, you could just parse it like just any other standard context-free grammar. And it has about 5,000 to 500,000 nodes in it and it a real one, a pricing graph. That's what it's called. It's called a pricing graph. And it represents anywhere between 100 to 10 ways to 30 solutions. So how do you make sense of this? Well, let's take a much more simpler instance of this for you to understand what is going on. Consider this pricing graph, which is a lot easier to read. What it shows are flights. Says you've got two choices for your journey. You could either take the left and or the right and. Let's look at the right and clause. The right and clause pretty much says you can take the flight NW21 and one of the two fares, the QE14 fare for 300 or the HE7 fare for 200. So that, or go back, the other choice, which is the other and, is you can take either AA10 or AA63 for a Y fare of 600 or an F fare of 1,000. So now the question is, well, you want to find the cheapest price. Well, cheapest is not always a good metric to go by, because I could give you a cheapest price that takes you 24 hours to go 50 miles, which is probably not what you want. So we come up with a utility function. We come with a utility function that says the cost of a journey is 1 times the price of the ticket plus 25 times the journey time in hours. So when you do that, say AA10 takes 5 hours, in which case the cost is 125. AA63 takes 6 hours, so the cost is 150. So $600 fare, the cost is 600. $1,000 fare, the cost is 1,000. NW21 takes 7 hours, so the cost is 175, and so on. So now let's start propagating these values from the leaves upward. So for an OR clause, you end up propagating the smaller of the two values. So between AA10 and AA63, the smaller of the two values is 125. Between $600 and $1,000 fare, the smaller is 600. Between the QE14 and the HE7 fares, the smaller is HE7 with 200, so you propagate 200. Now, you take the AND clause. For the AND clause, you pretty much add the two costs. So on the left-hand side, the AND is 125 plus 600, that's 725. On the right-hand side is 175 plus 200, that is 375. And at the topmost R, you apply the same rule. If it's R, you take the smaller of the two, so you get 375. So that is your smallest price. The basic smallest price you can get is 375. And the way you get it is, again, just go down that tree. 375, go to the corresponding AND, which means that you explore both these edges, both the children. And at the R, you explore only one of it, which corresponds to the value there. So now the cheapest, the quote-unquote best price you have within this graph is NW21 for $200. Right? And another thing that you can do here is you can sort of propagate these values up and down the tree and get things like, for example, I've got AA10. It takes 5 hours. So what solution is it a part of? What are the solutions it's a part of, and what's the cheapest solution it's a part of? And you can sort of propagate it up and down, and you can do what is called sort of inside-out solutions, like marginal posterior calculations. I mean, these are useful because, for example, if you say, no, I have to take this particular flight, now tell me the best prices that you can give me with the restriction that I have to take this flight, and so on. So this is, and this data structure here at QPX helps us sort of solve these, do these searches very, very quickly. Although we cannot guarantee you that we'll get you the best solution, because as you know, the problem is really hard, and in fact, the full search is pretty much Turing undecidable. But we can do our best, and we can give you answers that are pretty close and that are actually pretty satisfactory. So you can end up with actually a lot of efficient pricing graph algorithms using this data structure. Now you can get like the best. It's easy to get the best answer with some flights or fares filtered out. All you have to do is just suppress or delete those nodes corresponding to the flights or fares from this grammar, from this pricing graph, and just recompute. You can get the kth best answers by just, once you get the best answer, eliminate that solution and then run it again. Or you can get the number of solutions. You could do like what I mentioned as marginal posterior calculations, which says what is the best answer that includes this specific graph, or this specific flight, or this specific fare, and so on. But the problem is far from solved, though, because given like 120, given 10 raised to 20 valid solutions, which ones are interesting? For example, if you look at only by price, you will find that for any reasonable size, say, international search, you can get the first 100 cheapest only prices vary by about $5. And if I give you as a solution about 100 different solutions with just $5 difference between them, you will not be able to get much out of it. They'll just say, well, this doesn't help me. Like maybe if I paid just $10 more, then I would get a flight that is 5 hours shorter than what you're offering me right now for just $10 cheaper. I mean, like, I'm willing to pay that $10 more. So now the question becomes, it's not just about giving the cheapest ones, but giving the most interesting solutions. And how do you define interesting? Just the lowest, or the lowest in each cabin, like economy? What about mixed cabins? Like if I want to show that if you pay just a few dollars more, you could get a business class in one of the legs, but economy in the other. And also, even if I can narrow it down from 10 raised to 20 to say a million is still too many. How do you choose which among a million to show? People care about so many different things like speed, price, time of day, the airline that they go, the number of stops, which connecting airports they go to, and so on. And people don't always tell you, right? I mean, people have a lot of hidden preferences when they search. For example, when you search for an airline's fare, you may have certain preferences, but there's no way you're going to tell the search engine that these are all my possible preferences until it tells you something that says, oh, here's a flight that leaves at 3:30 in the morning. You're like, well, I don't want to get up at 1 o'clock in the morning to get to there. No, I want something that leaves at a reasonable time of day. But until the search engine gives you an absurd 5 a.m. result, you're not going to tell the search engine not to look for it. And this is what makes the diversity, solution selection diversity so interesting and so challenging. We would like to be able to show you the solutions that you would actually use, as opposed to show you a solution that makes no sense and force you to go through more searches. So that is sort of how we would mix and match solutions and give you a good diverse bucket. But there's still more problems here. Like we've got about 600 airfare taxes for about 209 countries. So when I'm computing a price, I have to take all of these taxes into account. And the taxes are written by legislators and bureaucrats in their native language, which means I have to first translate it into a language that I understand. But these laws are usually very ambiguous and often complex. I mean, you have no idea what they mean in a very mathematically formal sense. And worldwide, on average, you see about 2 to 3 changes in these laws per day. And this has to be coded by hand by a team of about 3-4 people. I mean, a handful of people. And often you must know the entire trip before determining what the tax should be used. For example, if you're buying a ticket to India, the tax that you're going to apply will depend on whether you're flying through Germany or you're flying through the United Arab Emirates. That determines how much tax you pay, because the tax for Germany is different from tax for tax through some other airport. And these tax amounts are not small. If you look at any ticket that you buy, tax amounts to a substantial percentage of the ticket that you buy. So this makes it really problematic. And not to mention, when you're buying across international travel, you're buying across different currencies. And the airline industry has its own standardized currency conversion process, which means now the tax has to be levied on the local currency and then converted to your own currency where the ticket is being priced, and then converted to a different currency with which you're actually going to pay for it. These things make it complicated. And these things make it a very, very challenging problem as is right now. But moving forward, it's getting even more interesting in that the airline industry itself is changing. It's becoming increasingly harder to compare trips. For example, now you've got one economy ticket that costs $25 more than another economy ticket, but the cheaper economy ticket has a baggage fees of $50. So which one's cheaper? It depends on whether you're carrying baggage or you're not. Meals in some cases are paid, other cases you have to pay for it. Now you have airlines offering paid seat assignments. That is, they say, oh, if you want a seat on the exit row that has a little bit more legroom, you have to pay $15 more. And now you've got this whole bundling or unbundling feature, which says, oh, get this and buy something else, buy a meal along with the ticket now, and it costs you less, and we're going to bundle all these things together. You've got something called personalization, where airlines are considering, the consortium is considering going, well, maybe we should have a different price for a frequent flyer versus somebody who's not a frequent flyer because they're a loyal customer. And the industry groups are working on a new standard, for the pricing to be passenger specific. If you have a passenger specific pricing, then the search you do may not yield the same results that somebody else does. And this makes an already complicated problem even harder, because we cannot share search results. We cannot say, hey, somebody else searched for the same ticket earlier, let me give you those prices. Can't do this anymore. So this is essentially what we're up against, and this is what keeps us, in some sense, up at night, or at least keeps the problem interesting and keeps us working on this. And there's a never-ending set of challenges and problems that make this space a very exciting one to be in. So with that, I'm going to end my formal part of the talk, and I can start taking questions.
We already have quite a few interesting questions in the group chat here.
Okay. All right. So let's see in the group chat. Okay, so Jitin asks, so does the algorithm actually divide each travel space into small segments and analyze them to see the cheapest rates? Even the round trip option actually doesn't line up with what the lesser distant way was. Well, no, it doesn't actually divide the travel space into smaller segments. It takes the entire travel space into account. It has to, because you cannot look at one leg, compute the best price for it without knowing anything about the other leg, and without knowing what tickets you're considering on the other leg. So you have to consider the entire thing into account. The only thing it doesn't do is consider the entire space, problem space. It uses some pruned problem space to say, well, I'm going to search only across this problem space. For example, if you're flying from San Francisco to Boston, you could potentially have a ticket that flies you to Tokyo from Boston, and then Tokyo back to San Francisco. And we could sort of prune all of those out and then say, well, we're going to reduce this, and we're going to reduce the space to something that's manageable, and then try to do something that's reasonable within a given amount of time.
So, sorry, this may be a bit out of order, but one of the questions that Sarah had asked is, does the place from where one buys the ticket affect the costs? And also, do the search engines, since search engines are taking your current location as the default source?
Yes. As a matter of fact, it does. In part because of the taxes that apply everywhere. I mean, buying a ticket in the US means it's a transaction that's happening in the US, and you have different set of rules for taxes that apply to the US as opposed to when you're buying it from India. And you also have the currency. If you're buying it in the US, you pay in dollars. If you're buying it in India, you pay in rupees. And remember, the airlines have their own currency conversion process, which is different from your standard exchange rate. So yes, that would affect the price.
And the government asked, is there a way to restrict the problem that you've been describing previously?
Restrict the... Well, yeah, of course. We could restrict the problem, but then you wouldn't be solving the problem that people care about. That's the real issue here. Like, if you restrict the problem to make it something simpler, easier to solve, then you will not get the solutions that people could use.
Got it. And Nikhil had asked, going back to the basic graph that you had showed earlier, does solving that have some relation to the AO star algorithm?
Solving the graph? The pricing graph?
I believe so.
No, it does not. This is a very different kind of problem. Here, what we're looking for are just navigating the graph itself it's actually quite time consuming. It's not like the AO star algorithm where you just go ahead and take the transitive closure. Like, this is very different from that, because we're not just taking the transitive closure. We're doing many more computations than just taking the min or max, because we are trying to produce a diversity of solutions. For example, the cost function is different when you consider things like, well, I want to prioritize price. And then you say, well, let me prioritize price and give you 3 solutions. And then let me prioritize the duration and give you another set of solutions. Let me prioritize the number of hops and give you another set of solutions. So it actually does a lot of these things together, but conceptually you can think of them as running them in different runs, but it runs all of these things together. So it's distinctly different.
And now we have something asking about a matrix. So Jason is asking, so is Google using the matrix flight search that we developed with ITA along with QPX? More specifically, is matrix the basis of Google Flights?
So matrix flight search uses QPX. Google Flight Search also uses QPX. They're different products. And Google Flight, the basis for Google Flight Search essentially is QPX in some sense. It's not so much Matrix. Matrix is a different product. But that also uses QPX.
And then we had a bit of a meandering conversation earlier about the fair basis codes. And I'm going to try to distill down some of the remaining questions from that. I think most of that had been answered. Sujay and GT, my apologies if there's still some, if you'd like to clarify the question on that, if you have still questions remaining. I'm going to jump instead at the moment to Julie's question. Do the airlines exploit the complexity of their ticket system to keep control of the market?
Yes and no, in the sense that airlines do use the complexity to their advantage, in the sense that they see how the market is behaving, and then they control the prices accordingly. For example, I think this happened recently, or a couple of years ago. There was one major operator in a commuter market. I think it was between Philadelphia and New York or something like that, I forget. So one, I think it was United, one major airline was, there were multiple major airlines operating that. and the prices were like $100 for that commuter market. And then one major airline decided to pull out of that commuter market, and the other airlines just immediately jacked the price up from $100 to $300 straight. And when asked about it, they said, well, the market is different now. We don't have as much competition, so the pressure to keep the price low is not that high. So we can go ahead and raise our prices. In fact, there were a lot of Senate hearings, I remember it came up in the Parliament, or the U.S. Parliament, and there were a lot of discussion, and there were the congressmen, politicians were almost like pleading the airlines to say, don't do this, you're going to kill the businesses, because they depend on these fares to do this. But the airline said, no, this is how business runs. So yes, they do exploit that, along with many other ways to control the market, because essentially they are the market. Right? You have all of these airlines that are vying for control of a limited market, and yes, they do that. There are some questions in the Q&A app. There are a couple of them.
Oh,
so let me start with one of them. Let's see. Will the airlines provide different rates to different providers? At times, I've seen different airline search engines provide different rates for the same flight combinations. This is not always, at least I don't know when they provide different ones deliberately. Sometimes you do have a sale that an airline offers for a specific travel agent. For example, you could have American Airlines offering an Expedia sale only on Expedia.com. But what you're seeing is probably the consequence of the change in seat availability. When the seat availability changes, it changes at one point and then rolls out through the entire system across different search engines. Some of them pick it up earlier, some of them pick it up later. And it can vary, right? Sometimes it could take hours for this rollout to happen, depending on what the network condition is, depending on how loaded the server that's rolling out these changes are, and so on. So when you're querying it at that time, and remember, seat availability changes continuously. So when you're querying during that change, one of the search engines may have the old availability, the other one may have new availability, and based on that, you might see different prices. And in fact, what happens is, say an airline has the old a search engine has the old availability, and it was a cheaper price. You bought it. The OTA, the online travel agent, like Expedia, whoever, honored it, sold you the ticket for that price. And then, in fact, a lot of times, even the airlines are not really sure what the current price is. So even the airlines will honor it. And then every so often, say once a quarter, they do an audit. And in that audit, they go ahead and take all the tickets that are sold, and they look at what the price should have been for those booking codes at that time. And then they go ahead and say, all right, so in case A, you overpaid, say Expedia overpaid a client. In case B, they underpaid for a ticket, and so on. And they come out with a balance sheet. It could be like, for example, United may go in and tell Expedia. I mean, I'm just making up numbers here. So it may take, airline A might go to a search engine B and say, you owe us $250,000 for this for these 3 months because of all these underpaid tickets. And then now it becomes a question of business negotiation, because even the airlines and the travel agents know that there is no way this data could have come in fast enough. And so they go ahead and sort of make this into a negotiation process, which then gets resolved eventually in some other way. But that's sort of the long explanation for why you see what you see in different prices, and how, in the back end, how it affects business. All right, there's another question. The second question here on the Q&A. Let's see. All right, it says, so can there be a situation in which a passenger pays more for a seat and some other passengers pays for the same set of seats of a particular code due to availability dynamics? Absolutely. That happens all the time. Like, you have a booking code, but you also have the fare associated with that booking code, and you can change that. There is no reason that couldn't happen. And also, it also depends on what the taxes are. It also depends on what other fares you're combining it with, and so on. So yes, that can definitely happen.
There's a couple of newly added questions in the group chat.
Okay. Let's see. Okay, so Garima is asking, not all search sites have access to the same flight data. Also, airlines would keep some data private as well. So how does Google use the QPX in accordance with ITA to deliver the best results in minimum time? It is true that not all search sites have all of the data, and that does factor into some of the results that we provide. For example, let's take Southwest Airlines, which is a very popular airline, low-cost airlines in the US. Southwest Airlines says, we are not going to publish our data to anyone. Anybody who wants to buy a Southwest ticket has to come explicitly to southwestairlines.com and buy the ticket. So what do? Well, we just don't include those results in our search. We just don't even accommodate for them. But if we think that they may have good prices, we'll ask you to go contact them directly. We might. But other than that, we don't. So Google really does use QPX in accordance with whatever airlines have given us permission to use this. And the airlines that haven't given us permissions to use it, unfortunately, will simply not show up. And that could be one reason why, for example, if you're in China, you have a different set of search engines that do much better for domestic Chinese flight queries than, say, Expedia would, or Google Flight Search would, or someone else would. Partly because it's very difficult to have coverage over all the airlines all the time with high enough quality. And that's another thing that a lot of the search engines do, is that if they think that the quality of the data that's coming in is not good enough, then you would probably suppress that result. Because in the end, if you get a low quality result, then you click on buy and you actually go to the actual airline to say, hey, can I get this ticket for this price? If the quality of the data that you had was bad, then you probably will not be able to buy that ticket. And that gives a bad user experience. And so for that reason, sometimes the results are deliberately suppressed. So Nikhil's asking, what makes airlines make some tickets refundable and some non-refundable? Because sometimes even high-priced tickets are non-refundable. Why? It all goes back to availability dynamics. Typically, refundable tickets are more expensive than non-refundable tickets for the obvious reason, right? One is that people who buy refundable tickets are typically business travelers whose itinerary is not always fixed, who need the flexibility and so are willing to pay more for it. However, if you're looking at a market that is fairly crowded, that is fairly busy, which has a very high demand, then it is possible that certain non-refundable tickets become much more expensive than much more expensive than refundable tickets. For example, a different market that's related. Say, for example, take flying from San Francisco to Boston, and then you have from Boston, you have a smaller airport nearby. Let's say somewhere in Providence. Now, the only flights that go to Providence, the only way to get to Providence, say, is through Boston. Now, it might be the case that a non-refundable ticket to Boston is very expensive, but a refundable ticket to Providence via Boston is cheaper because it's not that easy to fill up that plane that goes from Boston to Providence. That's where they discount you for it. So some of these things, O&D availability and seat availability dynamics playing to each other, resulting in such what seems like bizarre behavior to us, but actually makes perfect sense within the revenue management model that the airlines follow. So here's another question by Jitin. Sometimes the airlines just show up their initial pay rate only in flight search, and taxes are never added till the payment window opens. So does QPX deal with that too? For the most part, QPX adds taxes. We have an entire module in place that adds taxes to all of it. And in case this doesn't happen, or in case you get a different price from the one that you were quoted, that would be a good time to raise a bug, or you provide feedback to say, hey, look, there's some discrepancy here. And
I would actually mention that if they send feedback, when you go on Google Flights, you can click on at least the help link, and then from there you can click on send feedback. And we take this really seriously on our team. Many of us already use every day, and so it makes a significant impact when we get feedback from folks that are using Flights.
Hello, sir. My name is Pawan. So my question is, how is this algorithm different from travel salesman problem? Because as you know, in the contents of the algorithm, you had mentioned that a flight should travel from one, it can go through one node just once, right? So how is it different from a travel salesman problem? I guess that algorithm was developed to solve a problem as such, right?
So a traveling salesman problem is a very specific instance of this, right? You can think of this as a variant of traveling salesman problem, but it's also a lot more complicated than that. Because typically a traveling salesman problem, first, we know that it's incomplete, so the best you can do are approximate solutions to it. But the second is that you have all of these, the availability here, the OND availability or the seat availability makes this problem very different because you cannot consider any approximate solution. You cannot have provably approximate solutions to it that easily. I mean, maybe there are provably approximate solutions otherwise, but here in a more restricted problem, but here I don't think you can find one, partly because the problem itself is queuing undecidable, whereas traveling salesman problem is not queuing undecidable. And also, you should also take into account that when you're looking for a flight, you're not just looking for a specific set of flights, you're looking for all possible flights across multiple future dates, because that's sort of how users search for it. Users say, well, I want to travel sometime in July for 1 month to some place, which is different from how a traveling salesman problem would be, which says, well, these are the costs, these are fixed, and given these fixed costs within this fixed graph, I want to go ahead and traverse this graph, minimizing some cost function. Unfortunately, the search problem itself doesn't have that because the costs themselves are not fixed. Not only do they vary with time, they vary with date as well. If there are no more questions, I guess we can then call it a day here. And everyone, thank you so much for joining in. This has been great. And if you have any questions, feel free to send me an email or get in touch with Deepak. He'll be sure to forward any queries to me. And I'm happy to engage with you further and answer any queries you may have offline.